angle and orthogonality in inner product spaces. What I did a few moments ago, I told you on last week that there are some pretty neat spaces that exist in the study of mathematics, that I wanted to include that in the discussion on last week. I went into the PDF for section 6.1 in Blackboard. If you care to go and look at that sometime. So in the PDF lecture in Blackboard for 6.1, I put in there, uh, I didn't take away, but I added some notes and comments. Back in 6.1, we talked about definitions, certain theorems dealing with the inner product, distances, and norms. And I went ahead and just made some reference to what these guys are called in a bigger sense of the study of mathematics. So you'll see some comments dealing with metric space and just a little snippet of what the metric space could be. It's more than this, but we start somewhere. Also a comment on Hilbert space and Banach spaces. So you'll see that in the 6.1 PDF. For 6.2, I added some more problems. I thought somewhat too lame of the problems that were there, and so I added about maybe 2 or 3 problems here toward the end, and we'll look at that today. First, we deal with a very classic theorem called the Cauchy-Schwarz inequality, which basically says that the positivity of the inner product is always less than or equal to the multiplication of the norms of the respective vectors. So the absolute value of the inner product of u and v is positive or equal to the product of the norms, the norm of u times the norm of v. You have probably, and I know you have from Calculus 2, when we introduced vectors, we ran across the cosine of an angle of 2 adjacent vectors. So here, so we can calculate not just the cosine, but even also the angle itself, in that the angle theta is the cosine inverse of this inner product of u and v over the norm of u times the norm of v. I think for most of the questions here in this textbook and also online, they just ask for the cosine angle. So it's just very straightforward here. It is that cosine that is just a natural phenomenon. What is not so natural is the Cauchy-Schwarz inequality. You can somewhat build the Cauchy-Schwarz inequality from the cosine. And let's just make a note of that, and then we'll move on. And for the life of me, I don't know why I didn't make space for that. Let's see if I can capture that. Push some of this down. I didn't mess up anything else. Yes, I did. Yikes. Everything else will be fine. Beautiful. Here, if you look at the cosine here, and we know that we know that cosine is between I don't know when that happened. I thought I adjusted it a few moments ago. We know that cosine is always between -1 and 1 and oscillates between those two. So we know that. So here the cosine is equal to this inner product. So this implies that -1 is less than or equal to the inner product of u and v over the norm of u times the norm of v. Now by definition, here the so-called, well, I don't want to make that jump right now. Just make that jump in just a moment. This implies multiply it through by the norms in the denominator. We have -1 or negative times the norm of u times the norm of v less than or equal to the inner product of u and v that's less than or equal to the norm of u times the norm of v. Now by definition of the absolute value, we have the absolute value of the inner product of u and v less than or equal to the norm of u times the norm of v. The definition that I referred to recall that the definition of the absolute value of x less than a is if and only if negative a is less than, it could be less than or equal to, it doesn't matter, less than or equal to x, less than or equal to a. So you can write it either or. So just from the cosine and how it's defined, the cosine theta is equal to this inner product, and we know something about cosine, that it oscillates between -1 and 1, you could somewhat really produce the Cauchy-Schwarz inequality from there. Well, the exact proof of the Cauchy-Schwarz is more involved in that, but this is what my professor would call an intuitive bird's eye look at the Cauchy-Schwarz inequality. Well, here, find the cosine of the angle between the vectors with respect to the standard inner product on the polynomial 2 space. So here, notice that P is a vector with components -1, 5, and 2, and Q is a vector with components 2, 4, and -9. So to find the cosine, we need to find the inner product, then also the respective norms. So the inner product of P and Q would be -1 times 2, or -1 times 2 is -2, 5 times 4 plus 20, and then 2 times -9 minus 18. This gives us 0. That implies, it doesn't really matter about your denominator. We know that our denominator is positive, so that does matter. But here the cosine is equal to 0 because it's going to be 0 divided by the norms of u and v. So just get 0. they don't ask for the angle, they just ask for the cosine. And that's how the questions are posed in the textbook again, and also in Wiley Plus. So, number 2, find the cosine of the angle between the vectors here with respect to the Euclidean inner product. So we find the inner product of u and v. So this is going to be 4 times 1 is 4 plus 1 times 0 plus 8 times negative 3. So here we get 4 minus 24 or negative 20. What about the norm of u? The square root of 16 plus 1 plus 64. The square root of 81, or just 9. What about the norm of v? The square root of 1 plus 9, or the square root of 10. So the cosine of the angle is the inner product of u and v divided by the norm of u times the norm of v. Well, the inner product we got was negative 20. And then here the norm of u is 9, then times the norm of v, and that was the square root of 10. That's it. So nothing more, nothing less. Just very straightforward algebra. Now, a very classic theorem here in the study of mathematics is called the triangle inequality. Now, I'll just go ahead and tell you what it says in a nutshell, and then we'll look at the illustrations and the proof of these two. This theorem, the proof of this, the question will be asked on the test. So you want to make sure that you can prove the triangle inequality for norms, and then also prove the triangle inequality for distances. Okay? The triangle inequality, have you heard of it before? Have you heard of it before? The triangle inequality, now you probably heard of it, hopefully you did, when you took high school geometry. Okay, yeah, so that's a while back. Longer for me than for you. And I'm trying to think myself, do I remember that in high school? I know going back and looking at the high school geometry book, it was in there. Whether or not my instructor went over it, it was in the high school geometry book. And what it says is so easy that you'll probably almost slap me for even saying it. Triangle inequality simply says that you have a triangle, you have 3 sides of a triangle. The triangle inequality says that the sum of 2 sides is always greater than the 3rd side. You've heard that before. That's triangle inequality. That's all it says. So given any triangle, you add up 2 sides, their lengths, that's going to always be greater than the other side, the 3rd side. That's all it means. We'll illustrate it, and then we'll prove it mathematically. So here, let u, v, and w be vectors in a real inner product space. Let k be some scalar by which in this setup for parts A and B, we don't necessarily need the scalar to show the triangle inequality. But it doesn't matter if there's a scalar multiplied through, you treat that scalar as you would some positive number with respect to those norms which you get out of that, the absolute value of a number. So let's illustrate that. Here, u and v are vectors, and so their respective norms would be their lengths. So I want to measure how long is u. It's the norm. I want to measure how long is v. It's its norm. And so if we start at some initial point, if we look at some vector u, And then we have over here some vector v. This length here for u is the norm of u, and then the length of v is called the norm of v. Now what I want to do is I want to add two vectors. Well, we take the tail of one vector and we add that to the head of the other. And that's how we add the vectors. So I take the tail of u and I add that to the head of v. Wherever I end up, it's said to be the sum. So here, the sum of u plus v is itself a norm. Now, what we've formed is a parallelogram. Taking that diagonal and slicing the parallelogram, we get two triangles. Just look at one of them because the triangles are congruent. So notice that the opposite sides would be parallel and also congruent, that is, measure the same. So up top, that red line up top is also the norm of v, and then this on the right side, that red line there would also be the norm of u. So pulling that out and just looking at one of these triangles, we have this. This is the norm of v, the norm of u, and this is the norm of u plus v. Triangle inequality. Triangle inequality says that the sum of the sides u and v is going to be greater than this third side. That's the norm of u plus v. Yes, sir. No. No. This class is for you an introduction to rigor. And anything that's rigorous is never a picture. Okay. But the picture is important and is good for us so that you have an idea of what's going on. The picture is always in the backdrop of your mind. So when we're working and calculating, I understand the picture. And so I know what I'm trying to get to because I got the picture in view. So here to prove this, we'll prove part A first. That is that the norm of u plus v is set to be less than or equal to the norm of u plus the norm of v. I'm going to square this. And here's the reason. One, if I square it, then I can get rid of the radical and just deal with the inner products themselves. At the end, I can take the square root and get back to the original form. So here, the norm of u plus v squared is simply the inner product of u plus v, comma, with itself u plus v. Right? I simplify that. I use the additivity property for inner products. And I told you that that's the same thing as the distributive property, if you will. So this becomes the inner product of u with u plus, it's going to be the inner product of u and v, then also the inner product of v and u. You add those together because we said that the inner products commute, right? So that's going to be plus 2 times the inner product of u and v. Is that fine? Can I just say that? Do you see what I'm saying? This is the inner product of u with u, the inner product of u and v, and this is going to be the inner product of v and u. Well, those two inner terms are going to commute, so they're going to be the same. This is just plus 2 times the inner product of u and v. And then that last one, when you FOIL that out, is the inner product of v and v, plus the inner product of v and v. All right. Now, start here. Just write the beginning again. This is equal to Now this inner product of u with itself is the same thing as the norm of u squared plus 2 times the inner product of u and v plus the norm of v squared. Are you with me so far? Okay. Now, this is less than or equal to the norm of u squared plus 2 times the absolute value of the inner product of u and v plus the norm of v squared. Why did I say less than or equal to? How do we jump from equality to inequality? Yes, sir. Right? This absolute value is what? Positive. The inner product itself could be negative or positive. So obviously, the absolute value is going to be always positive or equal, right? Greater than or equal. So here, this is by property of numbers. So now, this is what we have. We have the norm of u plus v squared is less than or equal to the norm of u squared plus 2 times the absolute value of the inner product of u and v plus the norm of, that's v, the norm of v squared. Now, this is less than or equal to the norm of u squared plus 2 times the norm of u times the norm of v plus the norm of v squared. So now I've jumped from the absolute value, 2 times the absolute value of the inner product of u and v, to 2 times the norm of u times the norm of v. How can I do that? What reason can we jump from one to the other? What tells us that? What was the first concept that we discussed in this class today? I don't want to take you back to your high school geometry days that you said that's too far to go back there. So let's just go back a few minutes to, I think it was around 1105, 1106. Anyone? We're saying that this statement here, the norm of u squared plus 2 times the absolute value of the inner product of u and v plus the norm of v squared is less than or equal to, and then I have over here in the middle 2 times the norm of u times the norm of v. Cauchy-Schwarz inequality. Look, take those 2 middle pieces. This middle piece here, that middle piece there. That's by the Cauchy-Schwarz. The Cauchy-Schwarz inequality says that the absolute value of the inner product of u and v is less than or equal to the norm of u times the norm of v. That's the Cauchy-Schwarz inequality. So here, our reason for justification is by the Cauchy-Schwarz inequality. So if that be the case, then I have the norm of u plus v squared, what I started from in the beginning, is less than or equal to the norm of u squared plus 2 times the norm of u times the norm of v plus the norm of v squared. This is equal to parentheses, the norm of u plus the norm of v, all to be squared. Just factor that, right? It's a perfect square trinomial, this statement here. So that is the norm of u plus v squared is less than or equal to, parentheses, the norm of u plus the norm of v to be squared. This implies, taking the square root of both sides, this implies that the norm of u plus v is less than or equal to the norm of u plus the norm of v. Daniel, do you see why the picture would just not be sufficient for the proof? So again, the sum of two sides for a triangle is always greater than the third side. Now part B, don't have much space, but I can probably put it all right here in this statement. Part B is the distance. I'm going to show that the distance between u and v is less than or equal to the distance between u and some arbitrary vector w, just any vector out there, and plus the distance between that w and v. So let's put the proof here. I'll leave the illustration for you. So here, the distance of u and v, this is equal to the norm of u minus v. Well, this is the same thing as the norm of u minus w plus w minus v. See how I got w? So saying minus w plus w is still saying 0. So w is just could be any arbitrary vector out there. So just adding and subtracting it, I haven't offset this statement. So this is the norm of u minus w plus the norm of, plus parentheses w minus v. I put the parentheses there just to show the emphasis of what I'm about to do, just to show associativity. And just putting the parentheses there, I hadn't changed anything from the previous statement. It's still saying the same thing. But I'm about to make a jump because I'm going to use here the triangle inequality for norms. Since I just proved part A, I can use part A to prove part B. I'm going to use this, the triangle inequality for norms, to justify this next statement, that this is less than or equal to the norm of u minus w plus the norm of w minus v by the triangle inequality of norms. See that? Think about this statement here. Think about that as just being u. Think about that as just being v. And so you end up with part A all over again. So that's going to be, that norm is less than or equal to the norm of the first part plus the norm of the second part. That's the triangle inequality for norms. I got to do some more pushing. No, I don't want you to pull that down either. I guess I won't. So let's see here. Um, and so this part here is equal to, let's see if I can put a hatch sign here, and let's see, I need to squeeze that somewhere. I'll put it here. That what I started with was the distance between u and v, and we have that this guy is equal to the norm of u minus w plus w minus v, and we have that this is less than or equal to the norm of u minus w plus the norm of w minus v, and this is equal precisely to the distance between u and w plus the distance between w and v. So that's the triangle inequality for distances. Well, orthogonality is a trumped up word for perpendicularity. Perpendicularity, that if two vectors are perpendicular, we say that they are orthogonal. And if they are orthogonal, that simply means that the inner products must equal to 0. Right? So the inner product of the two vectors. If that comes out to be 0, then you know that you're talking about two perpendicular vectors. The generalized theorem of Pythagoras. It's said to be the generalized theorem of Pythagoras. There's a theorem that the Pythagoras theorem comes from, and that itself is the generalization of the concept. The Pythagoras theorem is only case number 2. Case 1 is when, see where those second degrees here, you have one case where you have the norm of u plus v to the first power is equal to the norm of u to the first plus the norm of v to the first. And then you got the second case where the powers are the second power. And then the nth case is for nth dimension, that can it be shown that the norm of u plus v to the nth degree is at the same thing as the norm of u to the nth degree plus the norm of v to the nth degree. Well, we get close to accuracy given that the two vectors are orthogonal. If they're orthogonal, then the inner products cancel out or they go to 0, because the inner products for orthogonal vectors is said to be 0. So the proof of that is very simple. And so here, intuitively, so if we have the norm of u plus v to be squared, that this is equal to the inner product of u plus v, comma, the inner product of u plus v. You start with the same proof for the triangle inequality for norm. You start off with that and see what happens. This is the norm of u squared plus 2 times the inner product of u and v plus the norm of v squared. Well, this is equal to the norm of u squared plus the norm of v squared, because the inner product is 0, because the two vectors are orthogonal. That's it. What about the orthogonal complement? The orthogonal complement simply says that if you have some subspace we call W, which exists in some bigger space, in some inner product space V, and the set of vectors in V that are all orthogonal to every vector in W is called the orthogonal complement of W, denoted by W perp. It is standard and so if we have some subspace W, then we also can talk about, if it does exist, and typically it will, the space of all vectors that are said to be perpendicular to these vectors. Now, for a straight line in the 2 space, it's very easy to get the orthogonal complement. Simply, that's understood to be that if I have a straight line like in R2, if I have y is equal to 5x, and if this is in W, then y equal to negative 1 over 5x is in W perp. Are you with me? Because we remember from straight lines that the 2 lines said to be perpendicular if their slopes are negative reciprocals. Now, for spaces, so I put the disclaimer in R2, for spaces a little bit bigger than that, then we have to use some information that you picked up in Calculus 2. And I think I put a problem down here that denotes that, and I'll show you that in just a minute. Determine whether the vectors are orthogonal with respect to the Euclidean inner product. Just take the inner product. If the inner product is 0, then these vectors are orthogonal, and we're done. So negative 4 plus 6 minus 2 equals 0, so yes. Inner product of U and V, negative 2 minus 2 minus 2, negative 6, so no. Assume that Rn has the Euclidean inner product. Let W be the line in R2 with the equation y equal to 2x. Find an equation for the orthogonal complement. And so we just gave an example of that. So here y would be equal to what? Yes, Tyler. Oh, I thought you were going to give me the answer. You looked like you were ready to say something. Okay. So here, what's the equation that would represent the perpendicular space of the equation y equal to 2x? Exactly. Two lines to be perpendicular, their slopes must be negative reciprocals, right? And then the other statement was the two slopes multiplied must equal to negative 1. Right? Now, let W part B be the plane in R3 with equation x minus 2y minus 3z equal to 0. Find the parametric equations for W perp. Now, you did that before if you took Calculus 2, And you probably didn't know that you were doing that because the language of it was different. So let me see if I can build this and show you what's happening. That if you have any plane in R3, let's take this to be a plane here. Any plane in R3, if I have the equation that represents the general form of the equation there, if I look at its normal vector that we called in calculus 2, we called it little n. Little n is said to be the direction numbers from the space that is perpendicular to this vector shooting up out in space. So here we said if you take some point here in the space that we call, this is W, and the point that we classified was actually x naught, y naught, z naught, but I'm just going to say x, y, and z. The direction numbers here for this normal is said to be A, B, and C. So we said find the equation of the plane. The equation of the plane is no more than the inner product of a vector in the space with its orthogonal or its normal vector. So here, the equation of the plane is the inner product of x, y, and z, A, B, and C. Here, orthogonal, so the inner product has to equal to 0. Now when you look at that and you work that out, you end up with AX plus BY plus CZ equal to 0. Have you seen that before? Now, so anytime you're given AX plus BY plus CZ equal to 0, it could also even be AX plus BY plus CZ equal to some number over here, D. But if it's 0, that means that the plane is spanning out of the origin. Okay? That's the base. That's where we're coming from. If that be the case, whenever you see this, then look, the direction numbers for the normal vector is going to be A, B, and C. So what are our direction numbers here for this plane? For the normal vector for it, it's going to be 1, -2, and -3. You see that? You're talking about the equation of the plane that's on the surface, but it's being formed by its stand-up perpendicular structure that we call its normal or its orthogonal complement. In calculus 2, we didn't say orthogonal complement, we said the normal vector. Right? We were talking about the orthogonal complement and talking about its space. That is all the vectors that look just like it. So, it says find the parametric equations for W perp. Well, those equations look like this. X equal to AT plus X naught, Y equal to BT plus Y naught, and Z equal to CT plus Z naught. I told you that anytime we have a 0 there, that denotes that the vector or that the equation is being spun from the origin. So X naught, Y naught, Z naught is 0, 0, 0. What is A? What is B? What is C? This is AX plus BY plus CZ, so A has to be 1, right? B is negative 2. C is negative 3. X naught is 0. Y naught is 0. Z naught is 0. So they asked for parametric equations. This is the definition for parametric equations. So here, that means that x is equal to AT plus x naught. Well, this is going to be 1t plus 0, or just t. Y is equal to BT plus Y naught. Well, B is negative 2 times T plus 0. And Z is equal to negative 3T. Number 5. Can you explain to me this space right here, C, and then bracket negative 1 to 1? What does that mean? The C stands for what? Should I sit down? I need my coffee. I know. Let's have a spelling contest. I'm just joking. I can't spell either. No, sir. Okay, I'll just go ahead and tell you because you all are just really hurting my feelings right now. Capital C is continuous, the space of all continuous functions on the interval, the closed interval from negative 1 to 1. The bracket denotes closedness. If it was parentheses, it would mean open. Right? So the space of all continuous functions. Right? If you wrote this one, if you look at this space, the space of all continuous functions on this interval, right? That's a pretty big space, right? The space of all continuous functions on the set of all reals. Do you know what this is? You know what that means? You know what's in that? Typically, every function and every problem that you covered in calculus 1, 2, and 3. That is calculus. So your whole calculus experience can be summed up in just that one statement right there. Everything you know is there about calculus. So when I was in school, the professor said, I'm going to give you calculus 1, 2, and 3 in 2 seconds. He just wrote that up there. He said everything you need to know. Every function, every derivative, every integral is in there. Class is over. Not for you all. You got to stay, right? So, if you go back and look at the notes sometime for 6.1 PDF, anytime you define an inner product here with an integral, which we saw this before, the inner product on the integral is said to classify the basic property for the so-called Hilbert space. And if you even Google Hilbert and look up, you know, he was a student to somebody that was very famous, and then even one of his students was very famous in the genre of mathematics and science. Came from a very popular time in the study of mathematics. It says, show that these vectors are orthogonal. Well, you know, I've been working too much. Try to go ahead and work this problem out and show that the vectors P and Q, polynomials if you will, P and Q, are indeed orthogonal. Let me see what you get. Yes, right now, everybody, take out pens, paper, pencil, what have you. and you show me something. And I'm going to be like, what's that? I don't know if it's Marvel Comics or DC Comics. I think it's what's Iron Man. That's Marvel Comics, right? Iron Man. And then what's the dude that's like the gatekeeper? He's the black dude, tough guy. He never blinks. What's his name? Who? Oh, okay. I thought you said hot dog. You said Honda? Hamda. Okay. I'm from South Alabama. My pronunciation is not as good as you all's. But I'm going to be that dude. So you can't get out of class today. I'm going to be over by the door. You got to give me the right answer, before you get out. I'm hot dog or Hamda or whatever. It's two doors, right? Man. So here, you took that inner product of P and Q, the integral from -1 to 1 of x times x squared minus 1 dx. So the integral from -1 to 1 of x to the third minus x dx. So you get 1/4 x to the fourth minus 1/2 x squared from -1 to 1. And so that gives us 1/4 minus 1/2, and then minus 1/4, then plus 1/2, get 0. Right? The last problem, let V be an inner product space. Show that if U and V are orthogonal unit vectors in V, then the norm of U minus V is equal to the square root of 2. Do you think you can get that? You want to try that on your own? You have any idea? No idea? Well, the key is always in the premise of the statement. The premise of the statement typically has information that says that something is given to be true. In the premise of this statement, two things are said to be true. What are they? No, you're jumping to the conclusion. The premise is always in the if statement, right? You got a statement, you got a premise, you always have a conclusion. Both encompasses the entire statement. So there are two statements in the premise. Do you see them? That are said to be true. What are they? So okay, let's slow up. Y'all too fast. U and V are orthogonal. All right? Good. So now you want to kind of wrap your mind around what that means. U and V are orthogonal. Which means then that the inner product of U and V is equal to 0. Right? And then the second statement is that U and V are unit vectors. What does that mean? If a vector is a unit vector, then what? I got some Chinese chicken up in my office, and I want to try to go ahead and get to it really soon. Okay. And then again, this is leftovers because I had half of it last night and it didn't feel right. I don't know what it was. I don't know if it was chicken or something else. But anyway, didn't go down like chicken. It's cat or dog, but yeah. Ah! So if a vector is a unit vector, that means what? Its blank is equal to blank. If a vector is a unit vector, it's, If a vector is a unit vector, then its norm is equal to 1. Doesn't that define a unit vector? All unit vectors defined in the sense that if you take their norm, you get 1. Right? It doesn't mean that the vector is equal to 1. Its norm is equal to 1. I think with those two ideas in mind, you can get it here. If U and V are orthogonal, then the inner product of U and V is equal to 0. And since U and V are unit vectors, I'm just taking what's given, then the norm of U is equal to 1, and the norm of V is equal to 1. All right? So, I have the norm of U minus V, which you recall is the distance between U and V, but it's also the square root of the inner product of U and V, U minus V with U minus V. So if I square it, I get rid of the inner product. I get rid of, of the radical. So if I square this, this is the inner product of U minus V with itself. That's equal to the norm of U squared minus 2 times the inner product of U and V plus the norm of V squared. What's the inner product of U and V? What's this? It's 0 because they're orthogonal. So this is equal to the norm of U squared plus the norm of V squared. We said the vectors are unit vectors. So that means that the norm of U is 1, so this is 1 squared plus the norm of V is 1, so that's 1 squared. I get 2. But you started off with the norm of U minus V squared. That's equal to 2. Take the square root of both sides, you get the answer. Okay? Now, what's the premise behind that? Just a little bit of thinking, right? And all you did was to take what was given. You never jump to the conclusion. Always take the premise. Use that. Look at its definition. What does that mean? Work it in together. You should get the desired result.